few correction, you get, for example, a decrease in the estimate of the band gap, okay, which is somewhat opposite of what we were thinking of. Now, one may say, well, this is for strongly correlated systems. Silico is not really in that class, but the goal, as Boris said, is to have a computational approach that is good for everything. Okay, you don't want to be deciding whether or not your system is correlated one to start with, because you may even not know this at the beginning. So in this case, it was actually quite simple to understand what the problem is, because in silicon or in general semiconductors, the band gap is due to what? To the splitting between bonding and anti-bonding. So it's proportional to the overlap. And if you have a scheme that kills hybridization, you probably be killing the overlap as well and the gap with it. So we went back to the source of our model, the Hubbard model, and tried to add another term. Okay, this term is describe the interaction between electrons on neighbor sides. Okay, this is normally called V. Okay, the amplitude of this interaction, and we tried to include this in our corrective Hamiltonian and came up with this new function that now has an on-site interaction and an inter-site interaction. It's now difficult to realize that these two are in competition with each other. Okay, and this is evident if we compute the potential. So this part here tries to encourage the localization of electrons on atomic sites. This part here tries instead to favor the occupation of states that have finite components on neighbor side, so sort of bonding states. And of course, the competition between the two and the balance between these two parameters, these two interactions, will give you the character of the final ground state. So of course, the final answer will depend on what the value is for U and V. But fortunately, computing V is not a problem at all. It's actually a byproduct of the method I was showing you before. So you just need to look at the off-diagonal elements of that response matrices, and you will have V for free. And it works pretty well in the sense that if you apply now this plus U plus V correction to systems like silicon, you get correction in the right direction. So this is the decrease we had obtained with just U, for example, and now you see the improvement of the band gap in the right direction. Same thing for structural properties, although it's not, I think in one case it worsened a little bit the results compared to GGA or GGA plus U, but not very significantly. So it normally improves the description of this system compared at least with the normal GGA plus U. And of course, we have to make sure is the band structure. As you can see, you just get almost rigid shift that opens the gap a little wider. And of course, we have to make sure that this further correction didn't compromise the good result that we had with the plus U in systems where it works, like nickel oxide, and this is actually the case. We actually obtain better structural parameters for equilibrium structure parameters for nickel oxide with a new correction and a density of state that seems to be more consistent with available photoemission experiments. Another characteristics that these computational tools should have, it should be able to predict or to compute properties that are useful, that are comparable to experiments, and vibrational and structural properties are certainly among those. So earlier I mentioned the results we obtained, the good results we obtained for structural properties in iron oxide. Vibrational properties are important too. So the ability to compute energy derivatives of the Hamiltonian, whatever your model is very important. It is important not only to include a finite temperature effect, but also to have an idea of what single modes, what the frequency of single modes are. If you need, for example, to use that information to recognize what structural phase you're dealing with at different pressure, or if you're looking for a signature of some transition that may be very important. So this is one of the last things we have been working on. So extending density functional perturbation theory that's normally used to compute phonons in PWSCF or ab initio, let's say, across the entire brilliance zone to the DFT plus U ground state, and you can appreciate by sight that it has a very significant effect on the phonon dispersion. So this is actually manganese oxide, another material in this class of strongly correlated Mott insulator. And you can see that the GGA not only underestimates the frequencies, but largely overestimates these splittings between transverse mode in low symmetry directions. And this is partly taken care of by the application of these plus U terms. So again, this means that accounting in a better way for electronic correlation is important for a number of properties. You cannot really, in most cases, dealing with these materials, you cannot really use a standard approximation and be sure that everything is working or is predicting a good result. And this is an example. So of course, the wish list for creating this computational tool is still long, and this is just illustrating few steps in this direction. So a lot of work is still needed, and will take some while to complete surely. So last, I want to acknowledge people who have worked in the development of this extension, and the Quantum Espresso community, of course, the Minnesota Supercomputing Institute, and also NSF for some partial support. Thank you.
One property that I would be particularly interested in is the Higgs
Yeah.
And you said in the beginning several times you was very reliable, DFT plus U was very reliable method. Then I wonder what the word reliable means.
Yeah, that is an open question. I mean, the dependence of the total energy on you, basically, how to say this? It's a problematic point of this approach. In the sense that, in principle, you should use different U's if you have different coordination, different structural phases. But several times, I mean, the function, the corrective function that you're using is not flexible enough to allow you to do that. What this means, in particular, it's not that easy to convey in words. I mean, the difference between the two phases, for example, that you may want to compare, is not is not possible to capture in the difference between the two parameters that you're computing. In some sense.
I mean, a very practical problem that we have.
Yeah,
Where you keep U all the way to the atomic state?
yeah, I mean, not directly, but
Well, the problem is you're benchmarking in certain properties, right? But then you never know other properties.
yeah,
Would you please bring back this phonon calculation? I have a question. You show that clearly that you have to have these U parameters in order to get this right phonon spectrum. But how sensitive is your result, the dispersion relation based on the parameter you chose for the U? Let's just say if you gave 10% larger of U, how does that one reflect in the phonon frequency calculation?
so we've done a little bit of that, not many tests on that. It's still, I mean, it doesn't saturate. Okay, so it still changes.
It doesn't saturate.
Doesn't saturate to any phonon dispersion, such that if you further increase U, you still get the same answer. So it will still change. Okay, how much? I'm not sure. I'm able to say that if
So
it changes
is this
linearly.
U parameter same as the U parameter that you optimize the structure for the count structure calculation? So
Yeah.
in a way, do you adjust the U to get the best fit with the experiment, or
No. There's no fit. There's no fit. I obtain it from linear response. So I get the unit cell where I want to compute phonons. I do linear response calculation. I get the U and then recompute the phonon, compute the phonons with that.
else use a different U parameter, they may see different phonon. Is that right?
From who?
If someone else using the same
Yeah.
technology but with a different U parameter,
Yeah.
they will see different.
Yeah, that's why we compute it. I mean, we try to have a reference, I mean, at least a reference method to guess what the value for that parameter is.
Yeah, a related question though. How sensitive is the free energy to the different choices of U? I mean, clearly the vibrations are frequency of U, therefore
Yeah.
free energy. So how important is it for thermochemistry and phase diagrams, for example? So would it matter really that I have 5.25 electron volts versus say something like gas from atomic volume, which may be 4 electron volts? Would that make a big difference in terms of what the planetary interior to look like?
I don't know yet. We haven't computed yet. I guess it's that depends on summation over phonon, so it's a little bit less sensitive. I would predict.
It's as an average, basically.
Yeah, but
to get these boundaries or phase transition pressures, of course, that is very sensitive to you, and therefore the absolute value is then. But like in a absolute potential calculation, we don't pay too much attention to the absolute value of you. We are looking at changes in
Yes.
the free energy transporting, and I haven't, even for the FT calculations, I don't pay too much attention to calculation and that's for don't do that routine. I look at equation of state parameters. That's
Aaron, just make a comment in response to Peter's question. At least one test, which Matteo was also, I think, part of this work with, where we were looking at battery materials, which was nice because it was energetics of a redox reaction that is extremely well characterized. A lot of these materials, we're studying very complicated phenomena there. You know exactly what the answer is. If you don't use LDA plus U, your typical error was about 1 eV in calculating a lithiation reaction.